In this video, I will show you how to use ANOVA in R for doing A/B testing. For that, I will be using Prython 2.0 as my IDE, which allows me to code both in R and Python. And you can download Prython from the following website. For this, you will also need my project ANOVA_R that you can download from the following GitHub repo. Remember to also download the CSV file. And the idea of ANOVA is to do basically a test whether several groups have the same mean or not. So for example, if we have one group where we just have a standard website, another group where we change the background to red, another group where we change the background to orange, another group where we change the background to green, and we want to compare if, for example, the amount of purchases made on each one of those experiments that we served to different people, they provide the same, for example, average value for the total amount sold. So the output of the ANOVA analysis will, in essence and in principle, be yes or no, those means are the same or not. And then on top of that, we need to do an extra analysis to identify which combinations there are the ones that are different. Maybe it's the green background versus the standard one, or maybe the green one is relatively different from the red one. So we'll see how to do that in a minute. So in order to do that, I will use Prython, as I said, as my IDE. It allows me to separate my code into panels as I have here. In each panel I can put anything that I want, really. And the idea is to separate my code in an organic way where I do different things in different parts of my project I can navigate easily through it. The idea is that I have an in and out part, so whenever I connect everything to the out, it will be able to access whatever is defined there. So, for example, my dataset here is data to model, but where is it defined? Well, it is defined here, but because the out, this acts as an output, is basically sending all the variables here through this line, if you want, is sending everything into here, and I will be able to access any variable, anything that was defined in here. Also the library here that was defined here, I'll be able to access it. So in order to run this, I have three running modes. So run only one panel, run everything that's connected up to here. So if I had other panels that were feeding or connecting into in, I'll be able to run that as well. And the last one, which is the one that I will be using, is a run below. So this means that this panel runs and then everything that's connected to it below runs. So let's do that and see what happens. So that finished quickly. You can see here I see when the panel finished. The data frames that are detected by Prython automatically are shown next to the panel that created them. The same for the plots. These are standard ggplots that are shown here. The rest is pretty much the same. So the two things that I did here, which is very standard in the ANOVA type of exercise, is that I am showing how does the data look like in each one of the groups. So blue, red, and standard. So these are the three groups. This is a box plot, and essentially what I would like to see here is whether they look different or not. So I see that the variability in each one of the groups seems pretty much the same. Maybe for the standard one there's less variability, but that's okay. And the means seem to be different, but bear in mind that there is variability here. So it's unclear whether each one of the means, or these are the medians by the way anyway, but if the means are probably close to the median, if they would be included into the other box. So that's essentially the objective of the exercise, is to test that. The other thing that I'm using here is that I have another variable, and this makes things a little harder. So this coupon discount, which could be coupon discount or standard. So this is a variable that for me, in the experimental design, this is called a blocking factor. This is something that contributes to the variability of my experiment, but it's not something I'm interested per se. I'm not really interested in measuring the contribution of this, but I suspect there is a lot of variability that will be explained just because there is a coupon, we'll be selling more. So I will be adding this into my model, but I won't be paying much attention. So you can see what I suspected, that the fact that we have a coupon actually pushes the sales up by a lot, and the impact is pretty clear. So how do I define my model? There are several ways of doing the ANOVA model in R, but I'll be using the AOB function, which is pretty standard. So total, which is the variable that I want to model, and then the two variables that I have, pretty simple, and then the data frame, and then I do a summary. That was easy, right? Here I have a decomposition. So the F is the degrees of freedom. We're not interested in that. Sum of squares, mean squares, F value, and this is the p-value. So you can see that both p-values for the website and type are highly significative. This means that the means from the different groups should be assumed to be different, which shouldn't surprise anyone because, as we saw here, they're different. They're not lying on the same horizontal line. There is variability, yeah, but yeah, they seem to be different. There is not much more to be done here. We usually don't look at the mean squares or sum of squares. We usually just look at the p-value here, and yeah, seems good. But then the next part comes, which is, and this is how I separate things here. You can separate it as you want. I put the residuals here, the residual analysis. So one thing that we should make sure is that the residuals are reasonably normal. And I am not doing any kind of test. You can add some, there are some statistical tests such as the Harkey-Vera, or there are many other ones. But as you can see here, they look kind of normal. They also, this cuckoo line seems to be indicating they are normal as well. Ideally, I would like my data to lie as much as possible on this line, and most of it does fall in there, so I'm kind of comfortable with the assumption that the residuals are normal. Here in the fitted versus residuals, actually what I would like to see is that the variability is kind of constant, which seems a reasonable assumption here. Maybe 132 and 79, that seem to be, and 155, they seem to be like indicating there might be extra variability, but they're just 3 cases. So really, if you exclude them, I look at this and this tells me that the variability seems to be okay. Yeah, I don't see any weird thing. So yeah, this looks good. And yeah, finally, so we have our ANOVA. Our ANOVA told us that the 3 experiments yield, well, actually 2 experiments and a baseline, which is the standard case. It tells me that they have 3 different means. So that's the conclusion. But the question is, which ones are the ones that are different? Which are the combinations of these that are different? So that's the next question. We need to do several tests here. For long and complicated and boring reasons, the problem is that whenever we start doing a lot of tests, it's likely that some of the tests that are non-significative might appear significant just because we're doing so many tests. For example, imagine in Excel you had a lot of columns, and in those columns you added, for each column you added random values, and then you take the mean out of those columns, and then yeah, if you had 2 columns and you compare them, it's likely that the mean will be the same. But what happens if you have 20,000 columns of random values? You start comparing column 24 against 35, 35 against 480, so you start comparing all of them one against each other, and eventually you'll find some of them that are different just because of random chance. But the reason they're appearing is actually not because they're different, it's just because we're doing so many comparisons, right? So we need some sort of correction. This is the usual way of doing this, using the Tukey HSD function. So you can read more about it elsewhere, but essentially it provides us with adjusted confidence intervals, or p-values, for these differences. And as you can see here, we have the ones that are different. You can see that all of them are different. So red minus blue, huge difference. You see that the lower and upper confidence intervals don't include the 0, which is great. Yeah, this looks pretty good. So we can conclude that in the 3 cases, the differences between them are highly significative. Maybe the biggest one is between standard and blue. You see that minus 39 there. We can say, loosely speaking, that between blue and standard we get like $39 extra in uplift.